Today we're going to talk about triangles, trapezoids, and rhombuses, or rhombi. We're going to do that today. We're going to start with triangles. Area of a triangle is 1/2 base times the height. We know that. We've talked about that many times. It's critically important that we remember the base and the height are perpendicular to one another. So on a right triangle, they're very easy to find because when you have a right triangle, the base and the height are both legs of the triangle. So here I have two right triangles drawn. So this time the base and the height are both here. I also have an isosceles or an equilateral triangle here. Two sides are the same and make it isosceles. If all three are the same, it's equilateral. If I use the bottom as the base, you have to use the altitude, which the height or altitude, again, is perpendicular to the base at all times. On an acute triangle, that altitude or height will be inside the triangle. On an obtuse triangle, like the one in the corner, the altitude will be outside the base. And one of the common errors done by students is they will grab two legs of the triangle when they need to grab a base and the altitude. Base and the altitude. On right triangles, they are legs of each other. Again, the formula is 1/2 the base times the height. And orientation of the triangles does not matter. Again, I see that this is a right triangle, so again, I just know as long as I make the base 1, the height will be another leg of the triangle. And again, on obtuse triangles, if I call this the base this time, the altitude has to be perpendicular to that line. Alright? It has to be perpendicular. And we have to remember on those obtuse triangles, okay? And that means that you can select any of the three legs of the base as long as you pick the altitude that's perpendicular. So here we have our favorite triangle, a 3, 4, and we all know, since it's a right triangle, we have a 5. If we want to find the area of this triangle, again, we use our formula, 1/2 base times height. Since they're perpendicular, we simply have to fill in the 3 and the 4. And it wouldn't matter if you called it the 4 and the 3. Multiplication works both ways, we know that, so it ends up being 6 inches squared. And again, we can use this principle of area in other ways. If I reorient the same 3, 4, 5 triangle and I say find the shortest altitude in a 3, 4, 5 triangle, we first realize that congruent figures have equal areas. These are congruent figures, the top one and this one. They are both going to have an area of 6 inches. So I can immediately fill 6 inches in for the area of the triangle, and if I use 5 as the base, I can immediately fill that in there. That leaves just one unknown in this one equation. It leaves the 1 height. And again, we don't have to use trigonometry, we don't have to use SOHCAHTOA. We can find that by simply solving this equation. And if I want to know the shortest altitude, then I can solve the altitude for the 5 as 12/5 of an inch. Well, the three altitudes are 12/5, 3, and 4. And the shortest then is the 12/5 of an inch. We didn't have to do SOHCAHTOA, we didn't have to do a lot of analyzing. A very simple formula. If we move to a new problem, find the area of the acute isosceles triangle. It has two legs of 10 and a base of 8. And again, if you want to try this yourself, just pause it and do the work. But we also again know that the first thing we have to know here is that none of these legs are perpendicular to one another. So we have to first realize that when we drop the altitude here, it's going to bisect the base, since I called this an isosceles triangle. It's one of the properties. So we can use Pythagorean theorem to find the height. And again, the hypotenuse is across from the 90 here in the triangle. Finally, we now have the height and we have the base is 8. So we simply plug into our formula, 1/2 times 8 times the height of 2 times the square root of 21 centimeters. And we end up with an area of a triangle of 8 times the square root of 21 centimeters squared. Finally, again, the altitudes on obtuse scaling triangles can either be inside for the base if you use this leg here as the base, or they're going to be outside, depending on what you call the base. Where this altitude would be for this base, and finally this altitude would be for this base. Remember, you never use two legs in an acute triangle or an obtuse triangle. You only use the legs for finding area in a right triangle. Next we're going to talk about trapezoid. Trapezoid is not a parallelogram. A parallelogram, both sides are parallel to each other. In a trapezoid, only two are parallel to each other. The other set is not parallel to each other. And I have trapezoid A, B, C, D here, called out in the vertexes, with a base of B1 and a top length here of B2, and the height between CD and AB, the distance in between the parallel lines, is H. Again, to find the area, those are the only bits of information we need. I still think the best way to always think about all figures is to think of triangles. And a trapezoid is simply an object that can be split into two triangles. If I use the bottom as T2, the height is right here, again perpendicular to the B1, and again the same height could be brought out here and have it be perpendicular to B2. 1/2 base times height, well 1/2 base 1h plus 1/2 base 2h is the area of the trapezoid. If I factor the half out and I factor the h out, I end up with 1/2 times the quantity of B1 plus B2 times h, or the average of the bases, the median of the trapezoid times h. So here's a polygon or a trapezoid where I've made the 6 length and the 3 length parallel, and it's not an isosceles because the 4 here is obviously longer than this edge here, and it gives a 2. And if you want to find the area, the 4 is not required. So again, we start with knowing our formula. 1/2 times the quantity, base 1 plus base 2 times h. We simply plug in the 6 and the 3 for the bases, and the height of this trapezoid is 2. You do the math, 1/2 times 9 times 2, and you end up with 9 meters squared. And again, I also will remind you that you can always live on these 4 formulas: the circle, circumference of circle, rectangle, and a triangle. And you can treat this trapezoid simply as 2 triangles. Anytime that you want and you can't recall formulas, you can always break down to those 4. And you can always find the length of the lines you need by making these triangles. There's the base, there's the first triangle, and it's going to have a base of 6 and a height of 2, which is the first one. Second triangle is going to also have a height of 2, but it has a base of 3, and it gives you the same exact answer. The last figure we have today is a rhombus. A rhombus is simply a special parallelogram in that the sides are parallel on both sides, which means the angles are equal across from one another. The blue angles are equal and these red angles are equal. Also, it means that this blue angle plus the red angle sums to 180, the blue plus the red sums to 180, and the same over here. Blue plus red is 180, blue plus red is 180. The blue and red angles are supplementary. But a rhombus is special because all the sides are the same length. And what happens with that is if you draw the diagonals, a special thing happens on the inside. The diagonals meet at a 90-degree angle. And if we draw a triangle here, based on our discussion of triangles just a few seconds ago, we know that the base of the red triangle is going to be diagonal 2. We also know, because it's a parallelogram, that the diagonals bisect one another. So the height here is going to be half of the diagonal 1. So we're able to calculate the area of a triangle, of the red triangle, very easily. It's 1/2 base times height. Well, the base is D2. We agree that the diagonal 1 is bisected, so that's 1/2 D1. And you get an area triangle of 1/2 times 1/2, 1/4 D1 D2. Will we have the red triangle? Will we have an exact match on the other side? So for the area of the rhombus, we have to sum that. And that's summing 1/4 d1 d2 plus 1/4 d1 d2. d1 d2 is like terms, so you can say 1/4 plus 1/4, which is 1/2. So we can prove that the area of a rhombus is half of the multiples of the diagonals. It's half of the product of the diagonals. So let's apply that to a problem. And again, word problems often are the hardest. So a rhombus has an angle measure of 120 degrees, and its longer diagonal has a length of 10 centimeters. Find the area of the rhombus, round to the nearest tenth. Alright, so here's the picture of our rhombus. It has the longer diagonals 10, the 120 degree angles here, and using the triangle inequality, the biggest angle has to have the biggest leg across. We know our formula. Area of rhombus is equal to 1/2 d1 times d2, and then we're letting d1 equal 10 inches, so we need to find d2. Well, if I draw in green the other diagonal, and that's good enough. We know that this is 90 degrees. We also know that this will be bisected, so this angle right here will be half of 120, or it will be 60 degrees. So we end up with a triangle right here that is going to be 5 by x, 60 by 30, a 30, 60, 90 degree triangle. Well, we have our standard 30, 60, 90, 2, 1, square root of 3. We know we can set up the ratios. X over 5 will be equal to 1 over square root of 3. Solving for x here, cross multiplying and dividing, we have x is equal to 5 divided by the square root of 3. We can now bring that up because we know x, this height right here is x. Whoops. We know then that the diagonal, the second diagonal here, will be 2 times that, or 2 times 5 square root of 3. Now again, once you have diagonal 1 and diagonal 2, it is simply plug and chug time. 1/2 of 10 times 10 over square root of 3. Using my calculator, I found the area of the rhombus to be 28.9 inches squared. And don't forget square inches, because it's inches times inches. Practice these on the lesson. Come back if you need more help.